Swayam Prabha. Digital India. Educated India.
Right. Today's thing transportation problems, further examples, and as the name suggests, there are several cases which we have not discussed. In the very first class, we have only talked about the balanced transportation problem where availabilities and the demands, they are all equal. Also, if you recall those four assumptions that we have had, in fact, one of the assumption was that there are no restrictions of any source to supply to any destination. Now, suppose that we try to relax those assumptions and the balanced transportation requirements one by one, and try to see that what are the impacts of those kind of things. So the first thing that we shall be taking up is the transportation problem where the availability is greater than the demand. So in this particular problem, there are three factories and there are four warehouses. The factories are sending materials to the warehouses, and the unit transportation costs are given in the red color. So, if factory one is supplying to warehouse one, the cost is 21, say rupees per unit material transported. The availabilities in the factories are 15, 13, and the demands in the warehouses are 6, 10, 12, and 15. So if you see the total demand is 43, total availability is 47. So who should answer that how to obtain a balanced transportation problem? What should we do? Because you see the transportation problems are defined for the only balanced transportation problem where demand and availability figures are equal. So how to really bring it to a balanced problem first? What should be done? Yes. So basically this extra warehouse, what you are telling, it is nothing but a dummy. That is the word used. So dummy warehouse has to be added, and its demand should be how much? Its demand should be the balance of these 43 and 47. That means 4. Is it all right? So that's what we should do. And in our next slide, let us put that how to obtain a balanced transportation problem. Consider WD, a dummy warehouse with the excess demand. So we have put a dummy warehouse with the excess demand, that is 4. And when that is done, these demand and availability become equal, and now we have a balanced problem. So this is the thing, that when we have availability greater than the demand, then what is to be done is that we have to consider a dummy warehouse or dummy destination with the excess amount of demand, so that the problem is balanced again. Right, the problem is balanced, but one key question still remaining. What should be the unit transportation cost to supply from factory to the dummy warehouses? If you see here, they are all put zeros. Now, can you tell me what is the logic behind putting all zeros there? What is the logic? So basically, these dummy warehouse is actually does not exist. The answer that whatever we might be getting here, suppose one of these squares becomes a quantity of 4. Let's say F3WD becomes a quantity of 4. What does it mean? Does it mean that we are going to send from factory 3 to dummy warehouse a quantity of 4 units? Yeah, that is the answer. You see what really happens. I told this earlier also. When you model a real system, there is a real system and there is a model system. So these WD is a concept in the model system, but it is not a concept in the real system. So like initially, while you model, you translate the real system to the model system. At the end, you should again translate the final solution to the real system. At that time, the interpretation is that F3 will have unused capacity of 4 units. So either it means that it will have those 4 units put in inventory or stock or something, or it may not even produce those 4 units. Is it not? So that is the final interpretation as far as the real system is concerned. But we are talking about the model system right now, because once we have modeled the problem, we want to know how to solve it. So at the modeling domain, there is a thing called dummy warehouse, and F3 would send material, or F1 or F2 will send material to that dummy warehouse. Is it clear? So therefore the costs are all zeros. Okay, now there is a point here. The point is basically that, look here, suppose there is a restriction that F1 cannot send to WD, or F2 cannot send to WD, or F2 have to send to WD. You see, those are the certain peculiar situations those might appear. Is it not? So anyhow, those kind of problems we shall take later. At this point of time, let us go ahead with this. So how to, therefore, we have already got the balanced transportation problem, and let us proceed from here. Yes, some questions you want to ask? All right. Already those kind of things we already know, that to solve the transportation problem, certain knowledge is required. One is the UV method, which are like dual variables. So these are required to compute the Cij minus Zij values, and basically they represent the cost potentials. So the equation for the basic, though, in the basic variables, the cost potential difference is 0. That means ui plus vj equal to zij, and since that cost potential is not there, so ui plus vj is not cij minus zij, because there is no zij. So ui plus vj equal to cij itself. So that is for the basic variables, and for the non-basic variables, the ui plus vj will give the zij values, and therefore for non-basic variables, the cij minus ui plus vj would give the cij minus jij values. One thing is that the number of u's and v's, total number of equations obtained, are one less. So since only relative values are important, one of them has to be put to zeros. All these things we discussed earlier. Now, good initial solution, must be obtained right in the beginning. Otherwise, we have seen, if we use some other rules like northwest corner rule, then we have to have lots of iterations while solving the transportation problem. So what Vogel's approximation method does, it obtains the minimum penalties for not utilizing the best possible cells for all the rows and all the columns. And allocation has to be made in such a manner so that the maximum of these minimum penalties are avoided. Is it all right? And after obtaining that particular cell, we have to make the maximum possible amount. Thereafter, you have to cross out the row I or column J, as the case may be, and reduce the corresponding availability and demand by the amount assigned. Is it okay? So, ultimately, then you have to obtain till all the basic variables are obtained. Good. Once you know this, let us now use, please mute all yourself, all of you, because some noise is coming. Right. So let us put the Vogel's approximation method and compute the minimum penalties so that we can continue further. Quickly, I'll just explain the process very quickly so that it's a refresher for you. Minimum penalties are now computed for not utilizing the best possible sales. So what is the minimum penalty here for this particular column? Smallest value is 17. Next smallest value is 21. So minimum penalty is 4. Here the minimum value is 16. Next best is 18. So 2. Here it is 14 and 18. So 4. 13 and 23, 10. 0 and 0. So 0. You see, if supposing there are 3 values, and one is 0, other is 0, other is also 0. Now, which one is the best? Any one is the best. So suppose this is the best, this is the next best. So difference is 0, right? Suppose it is 0, 0, 5. Don't put a 5 there, thinking that two zeros are equal, so gap is 5. No, answer is not that. The best is 0, next best is also 0, so gap is 0. All right, and row wise 0 and 13, so 13, 0 and 14, so 14, 0 and 18, so 18. All right, so then we have to avoid incurring the maximum of these minimum penalties, and the maximum here is 18. So that means we have to choose this particular row, and best possible value is this 0, right? So we have to put some entry there. So you look at the availabilities and the demand and tell me how much should we enter there?
4.
4. Right. So 4 should be entered. Very good. So exactly 4 is entered. So moment 4 is entered, then this particular column is crossed out, and thereafter this 4 is also crossed out because it is filled up, and this 19 is reduced by 15. Now again you compute the minimum penalties. So this is 4, 2, 4, 10 and 0, and this side is 13, 14 and 18. Right, now comes the crunch time. Now tell me which one is the maximum penalty? Maximum penalty is 18, is it not? So best possible square is then this particular square, F3W3, and F3W3, we have to make some entry, and let us see that what kind of entry is made.
So the penalties need to be recalculated.
Yes, yes. Oh, I'm sorry. The penalties to be recalculated. So that is what, after this, it is this slide is only showing that how much is allocated. Very good. So after that, in the next iteration, this is the important iteration, the penalties are recalculated. So before this 15, right, let us hope that, the 15 is not allotted yet. So 13 was best, 16 is next best. So this is 3. 14 and 17, so 3. Then 18 and 27, so 9. And this side is 4, 2, 4, and here it is 10 because the 15 is allotted yet. So which one is the best possible value? I mean the maximum of these minimum penalties. Can you see it is 10? So which square should be, we should make some entry? 4, thank you. So F1W4. Now question is how much should we enter? You see this is 15 and 15. Both sides are 15. So row and column both get satisfied at the same time. This is the peculiar thing that has happened. The row and column both have got satisfied at the same time, and if we enter a 15 here, because we have no other choice but to enter 15, because that is the maximum that can be entered in this particular cell. So moment we enter this 15, we see this 15 is crossed, this 15 is also crossed. So should we put cross at the both row and the column? There are two methods are available here. You can put cross on both sides. If you put cross in both sides, then you are going to have an unique problem. What is that unique problem is that, there are 3 factories and there are 5 warehouses. So how many basic feasible solutions you are expecting?
4.
Not 4. 3
7.
plus 4
7.
minus 1. So 7, not 7. See, I'm sorry, 3 plus 5. There are 3 factories and there are 5 warehouses. So 3 plus 5 minus 1. That means 8 minus 1, that is 7 number of basic feasible solutions, or 7 number of basic variables you are going to get. Now, once you enter a 15 here, and if you cross out both row and column, you are going to miss at least one row or one column. So what is going to happen? You will be able to fill up this table not with 7, but with 6 only. Right? Now the question is, if you have less than the number of basic variables, in the thing, that is not correct. You have to have one more basic variables with a 0, right? So because the solution is degenerate, you are then going to have a degenerate solution. Anyway, even otherwise also you are going to get a degenerate solution. So the additional problem will be where to put that 0. So you have to do some exercise where to put that 0. We are not going to follow that method. We are going to follow a simpler method. The simpler method is that do not, although both row and column both have got satisfied simultaneously, but we are not going to cross out both row and column. Please remember this, that whenever the row and column both get satisfied simultaneously, we are not going to cross out both row and the column at the same time. We shall cross out only one of them. Now you can cross out the row or you can cross out the column. We are crossing out the column with a simple calculation that this 41 is very high, is it not? Here this 16 is better than this 23. So with that kind of consideration, although that may not mean much, we are then crossing out the column only and not the row. Right. So what we did, note that the row and column both got satisfied at the same time. We satisfy the column only. This will leave a 0 in the F1 availability. Is it all right? So what will happen? This side, this 15 is crossed, but this side, because we have not crossed out the row, so here the availability is 0. That means we can still make an entry of 0 in one of these three squares. Because we know a degenerate solution is going to come, that means we are going to get one of the basic variables as 0. We also know therefore that that basic variable 0 would be in one of these three squares. Is it not? So is it clearly understood that why the problem is degenerate, why a 0 has to be put, and why we are not crossing out both row and column together? See, you can cross out both row and column together. That method is also available. But we are not doing it because in this particular way, if you do, then after you get one less basic variable and you are facing with a problem of where to put the 0 and then put 0 in an arbitrarily independent square, that problem, the Vogel's method itself would help you in putting the 0. Have you got it? So either you follow a method where you cross out both row and column simultaneously, fill up one less basic variable, then you are left with the problem of where to put the 0, and then arbitrarily you have to put a 0 in one of the uh, independent square, because that is not making closure with any of the basic variables already considered. That problem you will be left with, and then you have to again put that 0 in one of the squares. But if you do not cross out row and column simultaneously, then the Vogel's method would help you in putting the 0. So is it clear, or you have some question here? Because this is an important concept all of you must understand. So have you all understood this particular method? If
Yes,
anyone
sir.
have any question, please ask. If you cross out both row and column simultaneously, what is going to happen? Please understand this. So suppose you cross, then this is crossed, this is also crossed. Then you have these 6, is it not? Now let us say only 2 entries are there. Now here probably you will be able to make some entry, let us say 6. Then suppose you make an entry of 4 here and 3 here, right? So 6, 4, 3, and then you have 2 more entries, right? So 2 more entries you will not get, because moment you get, I'm sorry, you might enter a 6 here and you might enter a 7 here. So supposing 6, suppose let us put even simple northwest corner rule to balance the remaining square. Suppose you have already filled up these rows and column. Then let me also put the pen. Let me show you. So this is the pen. So supposing you put a 6 here. You put a 7 here. you put a 3 here, and you put a 12 here, right? And you cross out this also. So how many entries are there? How many entries are there?
Six are there.
6, and see all
Six
are
and
filled up. Can you see that all are filled up? Can you see that F1 is
yes, sir.
15 total, F2 is 13 total, F3 is 19 total, this side is 4, 15, 12 and 3. See that it is all balanced. But how
Yes,
many
sir.
entries you require? 7. Now if you do
7.
not have 7 entries, can you calculate UIs and VJs? You cannot calculate UI and VJs, right? You cannot calculate UI and VJ coefficients because you do not have enough number of basic variables. Is it not? You have to have 1, 2, 3, 4, 5, 6, 7, 8, 3 UIs and 5 VJs. But you have only 6 equations. So 2 of them are not known. One you can put 0 because of relative values. What about the other that you cannot calculate? So if you cannot calculate UIs and VJs, you cannot calculate the Cij minus Zij values. So you can see that you are going to have a degenerate solution. So you have to put a 0 somewhere after getting this problem. Now the question is, where will you put the 0? Which square? Which is an independent square? See, this is not an independent square because it makes a closure. This is not an independent square because it is makes a closure. All right, so you have to really find out an independent square. So this 0 is an independent square. You can make a 0 entry here. So let's put a 0 there. So what you do, you make a 0 here, and make an entry. Then you have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 entries. But then problem is that why you put 0 here? Why not in here or here or here or here? So you see now, depending on where you put 0, that would depend how many additional iterations you are going to require. You got my point? So this is the problem that will happen, if you cross both row and column simultaneously. It is not that you cannot solve the problem. You can solve the problem, but then you are left with a problem of putting the 0 yourself in an independent manner. You got my point? Did you understand that
Yes,
what
sir.
you are
Yes,
telling? But instead, if you
yes, sir.
allow the Vogel's method to help you out, then you do not have that kind of problem left with yourself. Right. So having said that, let us now carry ahead. So what we have done, we have crossed out the column, but we did not cross out the row, and we put that 0 availability here. Normally we don't do it, but because the row and column both got satisfied simultaneously, we cross out only one and we put a 0 in this. Good. So now maximum of the minimum penalties are recomputed after putting this 15. So what are those penalties now? The penalties are 5. Then here it is 3 because this was not there earlier. This is not filled up yet. So 14 to 17, 3, 18 to 9, and 4 to 4. Rest are all gone. So this 0 is crossed out also. All right. So therefore that maximum possible penalty is 9. That means you can enter F3 to W3 something, and we put a 12 and then we cross out. So W3 column is also now satisfied. Now in the next table, again we recompute. So this is 5, this is 1. Before putting this 0, you have a 5 here, and here this side is 4 and 2. So obviously this 0 is the, this 5, one of the 5 have to be chosen. So we choose this 5, and then how much we can enter because 0 is here. So we put a 0 only. So look here, the Vogel's method has helped me to put that 0. Right, so we put that 0, And moment we have put a 0, we know that we are going to get a degenerate basic feasible solution. That means the solution that we are finally going to get is going to be degenerate. All right, so there is because we have a 0 in one of the squares. So that is how we have that, and then we continue further, and this time we find that an entry of 6 is coming here, and moment this 6 comes, then the rest of it become trivial, and we simply fill up the remaining quantities, that's 7 and 3. So this is how the basic feasible solution is obtained, and 1, 2, 3, 4, 5, 6, 7, all the required 7 basic feasible solutions are obtained also, and we have got the degenerate basic feasible solution with VAM. All right, so this is how the degenerate basic feasible solution is obtained. Then we have to, this is the degenerate basic feasible, and it is degenerate because one of the entry is 0. Thereafter, we have to call it the iteration 1, and UV coefficients are calculated. So because there are 3 entries, so I put a 0 here, and then because of this 27, we got 27. Because of this 18, we got 18. Because of this 0, we got 0. Then this one, and this one is obtained. But with this 27, we can calculate this as 11 and this as -9, because -9 is here. So with that, we can calculate this as 26, because this plus this should be 17. And because of this -11 and this 13, we make this 24. All right. So once again, we got a revisit of how to compute UV coefficients. Cross check is also required. -11 and 27, 16. -11 plus 24, 13. -9 plus 26, 17. -9, 27, 18. 0 and 27, 27. 0 and 18, 18. And 0 and 0, 0. So you should be having a knack of computing these UV coefficients quickly. And thereafter, for the non-basic variables, we compute. So 21 minus of -11 minus 26 plus 25 minus and minus plus 0 minus of -11, so plus. So ultimately, we find all of them are plus. That means the solution obtained from the VAM is optimal itself. So iteration 1 itself is optimal, and this is that final solution, and we say that all the Cij minus Zij values are now positive. So TC star, that means total cost, is now 720. That can be obtained by multiplying 15 into 13, 6 into 17, 7 into 18, 3 into 27, 12 into 18, and adding them. Why? Because that is the amount that has been sent, and these 13, 17, etc. are the unit costs. All right, so have you understood that how to solve a degenerate transportation problem? There will be a situation where both row and column get satisfied simultaneously, and when that happens, you know very well a 0 is imminent. There are two methods: cancel both row and column, solve the problem, you get one less basic variable, and then put the 0 at a independent square that doesn't make closure with any of the other basic variables chosen. The second method is let the Vogel's method itself decide where to put the 0, and that can be done by filling up only one of the row or the column when both get satisfied, and put a 0 value in the corresponding availability or demand, as the case may be, and continue and put a 0 at the appropriate place. Right. So this is how these kind of problems are solved. Now we are taking up the second problem, where we have availability greater than demand, but there is also a restriction. So as we have discussed earlier, that one of the assumptions in the transportation problem is there are no restrictions in supplying materials from any source to any destination. But if you relax that condition, then there could be restriction or restrictions, not one, but more than that. So what we put? We put an M for a minimization problem and -M for a maximization problem. So m is a very large value near to infinity. The idea is that that particular square, if you utilize in transporting material, it is going to create a lot of costs, and therefore that square will be not viable at all. So let's look at this particular problem where all the values are same, and this is the same problem that we have solved just now with an additional constraint that F3 cannot send to dummy. That means F3 material must be utilized by one of the real warehouses. That material, because F3 material is good and it cannot be wasted, right? So that means F3 cannot send to dummy. Now the language is also important. What language it is given? It may not be said that F3 cannot be sent to dummy. It might be condition would be that F3 material cannot be sent to has to be utilized, or F3 material has to be sent to one of the real warehouses, or the language could even be that F1 and F2 material can be wasted. You see, now that you have to understand from the logic, what is it that actually is told there. So essentially all those languages finally mean only one thing, that F3 material cannot be sent to WD. All right, that means this particular square is restricted. So what we should do, this is first we have to see whether it's a maximization problem or a minimization problem. We have not dealt with any maximization problem yet. In our next class, we shall do that. Let us say that F3 to dummy is not allowed. So what we do, we put an M there, right? So we put an M in F3 to WD. Now, once we put an M, and then these are Vogel's method once again. So we see again, we compute the penalties. So already you have seen the method. So here this particular penalty is different because the 18 not 0. So earlier it was 18. Now it become 18. 27 minus 18 equal to 9, and this side will be 0 anyway. So then the best possible square is 14, and then F2 to WD some entry has to be made. So how much entry? Again, you see that entry of 4 could be made there. So we make an entry of 4, and after making that entry of 4, we recalculate the penalties, and the penalties are now 13 to 16, 14 to 17, 18 to 27, and 17 to 21, 16 to 18, 14 to 18, and 13 to 23. So again we see that this 10 is the highest, and then again this square is chosen, and again we have that row and column satisfied simultaneously. So same situation has come again, and we can follow the same path, that is we enter a 15 there, make it 0 and cross out. It's all right. So like that we follow the Vogel's method, recompute the minimum penalties once again. So 5, 3 and 9, and 4, 2 and 4. And then we see this 9 is the maximum. So therefore we should make some entry here. It is very clear. How much entry should we make then here? What should be the value then? Is it not? That should be 12. Fine. So an entry of 12 could be made there. So that is made. That is the 12 is made. Then only these squares are remaining. And again, the penalties are recomputed. We find a tie. So tie is broken arbitrarily. Let us take this row. So we put a 0. So where to put 0? Because this 16, because 16 is the lowest value. So the 0 is also chosen. So only 2 more squares are there. And after that, we see that this is having the 17 because of this 15. So therefore we make some entry 6. Now the problem is trivial, and we don't have any further choices. So obviously we fill up the remaining squares, that is 3 and 7. And then we have 1, 2, 3, 4, 5, 6, 7 as the degenerate basic feasible solution. All right, so the degenerate basic feasible solution has been obtained in this case. Look here, F3WD was part of the optimal solution earlier, but not this time, right? So this is what has happened. And thereafter, this is the iteration 1. We compute the UV coefficients once again. And after computing UV coefficients, we find that all Cij minus Zij values are positive. This is also positive, somehow missed out. So therefore, we find that iteration 1 itself is an optimal solution. So we got the optimal solution. One very interesting thing is that if you calculate the total cost at this point of time, you see 15 into 13 plus 6 into 17 plus 3 into 18 plus 7 into 27 plus 12 into 18. This will come 0 anyway. So these total actually comes out to be 756. Now this is interesting. Earlier our total was 720. Now the total is 756. So what has happened? You see, any restrictions you put, you are definitely going to get a new solution. The new solution, however, will be worse than the best possible solution. That is exactly what has happened. Because F3WD, if you are allowed to use, obviously it has been part of the optimal solution. But we have put an M out there and we have restricted that particular square. So when we have restricted that particular square, and with that restriction, what we have achieved is we found a new solution nevertheless, but that new solution is not as good as the original solution. It is the total cost has gone up by 36. That is from 720, it has gone up to 756. All right, so this point has to be remembered. All right, now let us look at another problem. That is the last problem for today. That is what happens when demand is more than availability, the other way around. So we have already solved some problems where availability was greater than demand. Now we shall consider transportation problems where demand is greater than availability. Since demand is greater than availability, we have to balance the problem. So in this case, should we take a dummy factory or a dummy warehouse? So because the availability has to be balanced, demand is more. So warehouses are already on the high side. So we have to add a factory so that availability goes up and total warehouse demand and total factory availability becomes equal. Yes, yes. Please ask the question. Please don't think in a mechanical way. Think on a practical way. The practical thinking is, suppose you produce 50 units and your demand is 60 units. Can you supply? Answer is no, you cannot supply. Right? So basically the simple answer is that if your total availability is 50 and demand is 60, you will not be able to fulfill the demand. That means there will be some excess demand which will not be fulfilled. But we have to solve the problem. What we arbitrarily say in domain, those 10 will be supplied from a dummy factory. What does it mean? It will be not supplied. You see that anything that will be supplied from dummy factory is a oblique language to tell in another word that those 10 items will not be supplied. But then question is which 10 will not be supplied? Should we deprive warehouse 1 or warehouse 2 or warehouse 3 or warehouse 4? We don't know. So since we do not know, we should allow the problem to determine that. So the transportation problem, the optimality criteria should determine which warehouse should be deprived of those additional units. That means all the units that will be actually shipped from the dummy warehouse to the dummy factory to the real warehouses, those are the items that are actually, those are the warehouses who are actually deprived of units to be supplied. All right, so if you understood that, now here is the problem. There are 3 factories. Their availabilities are 11, 13 and 19. That means total is 43. and the demands are 16, 10, 12 and 15. That means total demand is 53. So as we have correctly diagnosed that this has to be balanced by adding a dummy factory, that is FD. So we added a dummy factory and now we have F1, F2, F3 and FD, and these are the the unit transportation costs. And since there are no restrictions, if we had some restrictions, then one of two would have been M. But anyhow, there are no restrictions, so we put all zeros and F1, F2, F3, FD, and we have a balance problem. And FD would has to supply 10 because the gap was 53 minus 43 equal to 10. All right, so this is the first step, that create a balance problem by adding a dummy factory so that the availabilities and demands are equated. Because demands are higher, a dummy factory is required. Good. So once we do, then this is how Vogel's approximation method. And thereafter we continue with VAM. We calculate the penalties. So here the penalty is 17, here it is 16, here it is 14, here it is 13, and here it is 3, here also 3, here it is 9, and here it is 0. So the highest possible penalty is 17. So we have to make some entry here. Obviously, the entry should be at FDW1. So how much should we enter? 10 or 16?
10.
10. Because 10 is the lowest. So an entry of 10 would come at FDW1. So exactly that we have put an entry of 10 here, and rest are blank. But you see the 16 is changed to 6 and this 10 is crossed out. One thing you must remember that what this signifies. It signifies that W1 has a demand of 16, but this 16 will not be met. Only 6 demand would be met and 10 items will come from dummy factory, which essentially means it will not come at all. Right. So this is our first iteration of the Vogel's approximation method. Now thereafter, we have to again compute the penalties. So penalties are recomputed. So this is become 4, this has become 2, this has become 4, and this becomes 10. And this side penalties will remain same because we have not changed anything. So now the best possible square is 10. And best possible, maximum of the minimum penalty is 10, and best possible square is F1 W4. So how much we can enter here? We can enter how much in F1 W4? So we can enter an amount of 11 in F1 W4, right? So let us put that 11. So that 11 is put. Now moment this 11 is put, then this 10 is also put. So now again the penalties are recomputed. This side no change, and this side these 3 should be crossed out then, and this side would be this has I think these penalties are not computed yet. So here it is computed. So this side is 15, this side is 9, this side is 4, and this side is 18. All right, and this side 3 is crossed out, so 3 and 9. So we are now having 2 rows left. So out of these 2 rows, then we see that this 18 is maximum penalty. So therefore we choose this particular column. The best possible square in this particular column is F2W4 because unit cost is 23. So this side is 4 and this side is 13. That means only an entry of 4 is possible at F2W4. So that entry of 4 is made, and therefore now W4 is also exhausted. And because this 4 entry is made, this 13 is changed to 9. All right. So only we have 6 more is to be filled up. So again we recompute the penalties. So these 17 and 32 15, 18 and 27 9, 14 and 4 18 4, and this side is 14 and 17 3, 18 and 27 9. So maximum penalty left is 50. So therefore we should choose this particular column. So F2W1 is now our best possible square, and we should make some entry there. So how much entry is possible there? So an entry of 6 is now possible, and that 6, if we enter, then this also will be filled up. So that's what we do. We make an entry of 6. So only now 4 squares are left out. The penalties are 9, 4, and this side is, the penalties are not computed yet. So this is where the penalties are computed. These are 4 and 9. Now, which one is the best possible maximum of the minimum penalties? You can see that this is 9 here and also 9 here. So there is a tie. So we have to choose some square. We have chosen F2W2. I mean, this 9 we have chosen column wise, and therefore F2W2 is the best possible square. How much we can enter? Only 3. So moment we enter 3 here, then we have no other choice. Then this is crossed out. Then we have no other choice but to put a 7 here and a 12 here. Is it not? Now, had we chosen this F3W3, anyway, the same result would have been obtained because we would have entered a 12 here. After entering a 12, this would have been crossed out. So then we would have got a 7 here and a 3 here. So the same result would have been obtained whatever method we may follow, whether we choose the column or we choose the row. Right. So this 3 is entered, then there is nothing else to do, and then the basic feasible solution is obtained. Now there are 4 factories and there are 4 warehouses. That means 4 plus 4 minus 1, total of 7 entries are required. How many entries are there? 1, 2, 3, 4, 5, 6, 7. Right. So 7 entries are there and they are all in the independent square. Because this independent square is very important. That is why it is a part of basic feasible solution, so that together they form a spanning tree. That means they don't make any circuit. They don't make any closure. Look here, these 3 don't make a circuit. These 3 don't make a circuit. So any 3 if you take, or any, there is no circuit. No circuit is completed. So, if you could get a closure, that means a circuit is obtained. So again, you see no closure here, no closure here. So, if you take in different ways, you can try. They are all independent squares. So if they are not independent square, you cannot compute UV coefficients. Now, whether your basic variables are rightly placed or not, it is a very good test is that trying to find out the UV coefficients. If you cannot find the UV coefficients, that means there is something wrong in your basic variable allocation, right? That means they have not been put in independent squares. So that is very important. So we are now in our iteration 1, and here is an example that the VAM may not give the optimum solution. VAM only give a good solution, and that solution need not be optimal. All right. So we compute the UIs and VJs. We put a 0 here, so we get a 0. With that 0, we get a 17. With that 17, we get an 1. And with that 17, we get a 6. With that 6, we get a 7. And like this. So then this 1 we get a 26. With this 26 we get a -8. So the UIs and VJ components are VJ values are obtained, and using them for the non-basic variables where there are crosses right now, those are computed. So all of them are coming out to be plus excepting 2 squares. So here it is 0 minus 0 minus 1. So -1. Here it is 0 minus 0 minus 6. So -6. Now tell me, where should I make some entry? So FDW4, we should make some entry. So let's put a pen and let us make some entry here. So if some entry is made, which one should go down? So FTW1 should go down. Which one should go up? So this should go up. And if this goes up, which one should go down? Correct, this should go down. So you see, you have to be carefully finding the closure. This closure is important to find out. And supposing you would have increased this and then you thought, okay, let me decrease this. But you cannot decrease that because if you increase this and you want to decrease that, then you have nothing to increase. All right, so that have to be aborted. So you have to be careful to find the closure. And once you find the closure, we have to then see which one is the minimum out of them. And then you see this 4 is the minimum out of them. So that means 4 should be, moving here. So this 4 as it moves here, this 6 will become 10 and then 10 will become 6. All right, so this is how the iteration 1 will be completed. So exactly the same thing is shown here, and thereafter that new iteration is obtained, that 4 is come here. Again the UV coefficients are recomputed, so 0 will give 0, this 0 will give 17, this 17 would give 1, this 1 would give 26, this 26 would give -8, this 0 would have got another 0 here, and this 0 would have got 13. So all the UV coefficients are obtained, and do not forget to cross check, right? Always cross check 13 and 0 13, 17 and 0 17, 17 and 1 18, 26 and 1 27, 26 and -8 18, 0 and 0 and 0 0. So this cross check is very important. Suppose you have made some arithmetic calculation mistake, then at the cross check you can correct them. All right, so after doing it, then the non-basic variables Cij minus Zij values are all coming plus, but this one is minus 0 minus 0 minus 1. So one minus entry is there. So some entry has to be there. So again, let us see how the closure is obtained. The closure, if some entry is here, so which one should go down? Again, you are saying FTW1. Yes. So this should go down. Which one should go up? This one.
F2W1.
Yes. And then which one should go down?
F2W2.
Right. So closure is obtained again. All right. So this is important. And the minimum to go down is 3. That means 3 should come here. All right. So like this, it is to be done. And after that, we see the same thing. This is how the closure is obtained. And then the third iteration is done. This 3 has moved here and other values are also changed. All right. So now iteration 3 is completed. And after that, again, the UV coefficients are computed. So 0, 0, 0, 0, and this 0, 17, this 0, 27, and this 27 is -9. So all are computed. And then for the non-basic variables, when we compute, and then we get all the, all of them Cij minus Jij values as positive. That means the, optimum solution has been obtained. And these optimum solutions, so this is our final solution, and the total cost of this solution is 769. This 769 has nothing to do with those earlier values because after all, this is a different problem altogether. All right, because availability and demand values are different. All right, so this is how you solve these kind of problems. Now there are other kind of problems which we are calling the special cases of transportation problem. So there could be situations where the demand pattern and the availability pattern may be different. People may say that I want as much as possible. So those kind of constraints could be there. Then we have not solved yet the maximization problems. So maximization problems are to be seen. And also we have to see other kind of problems like aggregate planning problems. All right, so there are lots of issues that are to be there, and there are also transshipment problems that is to be discussed. So all those things we shall discuss next week. Right, so thank you very much.